I am Anudaya, a student of BSc first year chemistry honors. Today I am going to read the chapter Alkanes. So here is the general introduction. The organic compounds containing only one carbon and hydrogen are called hydrocarbons. These are of two types. First is open chain or acyclic hydrocarbons, and the second is closed chain or cyclic hydrocarbons. The open chain or acyclic hydrocarbons are also called aliphatic hydrocarbons. These are further of following types: alkanes, alkenes, and alkynes. The compounds which have only carbon-carbon single bond and have general formula CnH2n plus 2 are called alkanes. They are also called paraffins, which is a Latin word meaning a little reactivity. Due to their low reactivity towards most of the chemical reagents under ordinary conditions, they are called paraffin. The alkanes have low reactivity due to absence of reactive site, in a sense double bond, triple bond, and any functional group. For example, methane, ethane, and propane, having one carbon, second, 2 and 3 respectively. General formula for aliphatic alkanes is CnH2n plus 2, and for monocyclic cycloalkanes this is CnH2n, and for bicyclic cycloalkanes this is CnH2n minus 2. Now here is the topic: types of alkanes. The alkanes are of three types. First is normal alkanes. Yeah, means single chain. The straight chain alkanes are called N-alkanes. Second is isoalkanes, the alkanes in which only one CH3 group is present at second position of carbon. It means the second carbon of the main chain are called isoalkanes. Neoalkanes are those in which two CH3 groups are present at second carbon of the main chain. So these are called neoalkanes, as shown in the examples. Now the topic is IUPAC naming of organic compounds. The IUPAC name of organic compound contains the following parts. Complete IUPAC name is written as 2 degree prefix plus 1 degree prefix plus word root plus 1 degree suffix plus 2 degree suffix. So in 2 degree prefix, it tells about the nature of substituents. 2 degree, in a sense functional group. Then 1 degree prefix tells whether the compound is cyclic or acyclic. Use cyclo before alkane if principal chain is cyclic. Then word root. Word root tells about the number of carbon atoms present in the principal chain. For example, meth, eth, prop, bute, pent, hex, and so on. Then 1 degree suffix. It tells whether the principal chain is saturated or unsaturated. Means it has a double bond, triple bond, or single bond. For single bond it is called ane, for double bond it is called ene, and for triple bond it is called ine. Then 2 degree suffix. It tells about the nature of 1 degree functional group. Some functional groups have prefix and some have suffix, so there are two positions. Then here are given rules for the IUPAC naming of saturated hydrocarbons. First is select the longest possible carbon atom chain, in a sense word root. Means you have to select the longest carbon chain. Uh, then the second is when two carbon atoms of equal length are possible, then select the chain having larger number of substituent. It means if there are two main chains having equal number of carbons, then we would prefer the chain having more number of substituent. Then the third is give the lowest possible number to carbon atom containing the substituent. It means we should start the naming from where the substituent is nearer to the first carbon. Uh, its B part is if there are two or more substituent, then the numbering of parent chain is done in such a way that the sum of locant is lowest. If there are two or more substituent, then the numbering of parent chain is done in such a way that the sum of locant is lowest. Okay, then the fourth is Fourth, first part is write the name of substituent before the name of parent alkane. Write the name of substituent before the name of parent alkane, and its B part is the position of substituent in the parent chain is indicated by writing its locant before substituent, and the locant is separated from the name of substituent by the hyphen sign. Then fifth rule is that when two or more substituents are present, then each substituent with their locant are arranged the alphabetical order. And then sixth rule is that if two different alkyl groups are present at the equivalent position, then the lowest number is given to the substituent whose prefix comes first in alphabetical order, provided that it does not violate the lowest sum rule. Then seventh rule is that when the same substituent is present at more than one position, then the locant of each substituent is separated by commas, and the suitable prefix such as di for two substituents, tri for three substituents, etc. are attached before the name of the substituent. Here is the point to be noted that the di, tri, etc. are now considered during deciding the alphabetical order of the substituents. The eighth rule is that when the substituent on parent chain is complex, then first, it is named as the substituent alkyl group. Second, the carbon atom of complex substituent attached to parent chain is numbered as 1 and so on. And the third is, the name of such complex substituent is always enclosed in the bracket to avoid the confusion with the locants of the parent chain. Then there are given some groups. First is alkyl. If the alkane has one substituent, then the remaining R fragment is called alkyl. Alkyl group is represented by R, capital letter R. It contains one hydrogen atom less than the corresponding alkane. So the general formula for alkyl groups is CnH2n plus 1. Then alkyl groups are named by replacing the suffix A and E in the name of corresponding alkane by YL. For example, for methane it's called methyl, for ethane it is called ethyl, and so on. Then the group is phenyl. If the benzene ring has one substituent, then the remaining C6H5 fragment is called phenyl. Aryl. If the benzene ring has more than one substituent, then the C6H4 fragment is called aryl. Then vinyl. If the ethene has one substituent, then the remaining CH bonded to CH2 fragment is called vinyl. Then allyl. If the one substituent is present on the sp3 hybridized carbon atom of propene, then the remaining portion is called allyl. Here are the examples. Then there are types of carbon atom in alkanes. So the first type is primary carbon atom. The carbon atom which is further linked either with one or no carbon atom is called primary. Then there is secondary. And the second type is secondary carbon atom. The carbon atom which is further linked with two more carbon atoms is called secondary. Then third is tertiary carbon atom. The carbon atom which is further linked with three more carbon atoms is called tertiary carbon atom. Then the fourth is quaternary carbon atom. The carbon atom which is further linked with four more carbon atoms is called quaternary. Here are the examples. This is 1 degree, 2 degree, 3 degree, and so on. Then there is given structures of alkanes. Electronic configuration in alkanes. Carbon atom in alkanes have electronic configuration as 1s2, 2s2 and 2p2. In alkanes, each carbon atom is sp3 hybridized. In a sense, each carbon atom satisfies their all the four valencies by forming only single bonds and are directed towards the corner of regular tetrahedron and the bond angle of 109 degree 28 minutes. So this is the structure of methanes. It looks like a tetrahedron as the carbon have only single bonds with hydrogen. Then the topic is structural isomerism. Alkanes show chain isomerism, which may be defined as a phenomena wherein some same molecular formula represents two or more compounds having different structural formula to the different arrangement of carbon chains. Such compounds are called chain isomers or skeletal or nuclear isomers. In alkanes, the first three members, like methane, ethane, and propane, do not show chain isomerism because only one arrangement of carbon atoms is possible in these three structures. But butane and higher alkanes show chain isomerism. So, first is chain isomerism in butane, having molecular formula C4H10. So, it has two isomers, N-butane, isobutane are isomers. Then second is chain isomerism in pentane. As the number of carbon atoms goes on increasing, the number of isomers will go on increasing. So pentane has three, and pentane, isopentane, and neopentane. Now here are chain isomerism in alkane, hexane. Sorry. So as I have told, uh, as the number of carbon atoms in the chain started increasing, so the number of isomers also go on increasing. Then there are methods of preparations of alkanes. First is from alkanes. The lower alkane can be converted into higher alkane by halogenation, followed by first Bose reaction, Corey-House reaction, or reaction with KCN, acidic hydrolysis, reduction with HI, red phosphorus, or reaction with KCN, acidic hydrolysis, NaOH, Kolb's electrolysis. So B part is the higher alkane can be converted into lower alkane by halogenation, followed by reaction with first aqueous KOH, concentrated HNO3 on oxidation, and NaOH, calcium oxide, heat, or second is reaction with alcoholic KOH, ozonolysis, or hot KMNO4, HI with red phosphorus, heat, etc. And then second is from unsaturated hydrocarbons. We can prepare alkanes from unsaturated hydrocarbons also. The alkene can be converted into homologous alkane by first is we can use different methods. So hydrogenation using finely divided nickel, platinum or palladium, जिसे बोलते हैं Sebezier and Sanderson reaction. और second is using water with H positive followed by Hi and red phosphorus, or third is using HCl followed by reduction using zinc metal with HCl. So this is how we can convert unsaturated hydrocarbons into alkanes. The methane cannot be prepared by this reaction because lowest alkenes and the alkynes have at least two carbon atoms. Because if we want the unsaturated hydrocarbon, two carbon atoms have double bond and a single carbon atom, it means methane cannot be prepared because at least two carbon atoms are needed to have a double bond between them. B is the higher alkenes or alkynes can be converted into lower alkane via ozonolysis or hot KMNO4 followed by reaction with HI, red phosphorus and heat. So this is how the reaction will go on. Its C part is the lower alkane can be converted into higher via halogenation followed by reaction with alcoholic KOH, NaNS2, RX or H2 with nickel. So this is how the reaction will go on. And D part is the lower alkynes can be converted into higher alkanes by reaction with NaNS2 followed by RX, H2 with nickel metal. Third is now the third method to prepare alkane is from alkyl halides. The alkyl halides gives corresponding alkanes on reaction with reducing agent like zinc metal with HCl or nickel with platinum, palladium or zinc copper with ethanol or sodium with ethanol or nickel aluminium metal with NaOH. So here is given the mechanism of this reaction. The reaction is believed to involve electron transfer from zinc to alkyl halide to form an alkyl carbanion which abstracts a proton from the acid or alcohol or sodium hydroxide to form alkane as shown below. So here zinc loses its electron and this electron is abstracted by the carbon chain. Mm, Then it forms a carbanion and this carbanion abstracts a proton from alcohol or acid and form alkane. Then the higher alkyl halide gives lower alkane on reaction with first aqueous KOH concentrated nitric acid on oxidation or NaOH with calcium oxide heat or alcoholic KOH with ozone or ozonolysis or hot KMnO4 HI with red phosphorus heat to give lower alkane. So this is how the reaction will proceed. The lowest alkyl halide gives higher alkane on reaction with sodium with dry ether heat Wurtz reaction. These reagents sodium with dry ether are used in Wurtz reaction. So gives symmetrical alkane or R2LiCu with heat Corey-House reaction. It is termed as Corey-House reaction gives unsymmetrical alkane. For symmetrical alkane we will use Wurtz reaction and for unsymmetrical alkane we will use Corey-House reaction. So this is how the reaction will proceed. Limitations. So now there are limitations. Unsymmetrical alkanes. In a sense, alkanes containing odd number of carbon atoms cannot be prepared by this method. Suppose it is required to prepare propane from a mixture containing equimolar concentration of methyl bromide and ethyl bromide, then along with propane, ethane and butane are also obtained. So Wurtz reaction is not used to form unsymmetrical alkanes and it is its limitation. Second is methane cannot be prepared by this method because methane contains only single carbon atom. And third is this reaction fails with tertiary alkyl halides. This reaction fails with tertiary alkyl halides because it started going on a different way. Wurtz reaction is very useful for ascending the series of organic compounds since it involves the formation of a new carbon-carbon bond. Here is its mechanism. Ionic mechanism. It operates when the reaction is carried out in solution. It has been suggested that an atom of sodium reacts with an alkyl halide to form an alkyl sodium compound having a carbanion character. The alkyl sodium thus formed provides a nucleophilic alkyl carbanion which displaces the halide ion from another molecule of alkyl halide by SN2 mechanism resulting in the formation of an alkane. This mechanism also explains the formation of side products, for example, ethyl iodide on treatment with sodium metal in the presence of ether gives N-butane as the major product and ethene as the side or minor products. So this is its mechanism. We have alkyl halide and react with sodium metal. Then a carbon ion is formed along with sodium ion and this is how the reaction will proceed. Free radical mechanism. When the reaction is carried out in vapor phase, it can take place via a free radical mechanism. Sodium metal first react with alkyl halide to form alkyl free radicals, which may couple or disproportionate to form the observed products. For example, if the alkyl chain is CH3CH2, coupling reaction yields a higher alkane. For example, butane. Disproportionation reaction from alkane and alkene gives ethane and ethene mechanism. The alkyl group of alkyl lithium displaces halogen from copper halide to give alkyl copper. Alkyl copper reacts further with alkyl lithium to form dialkyl cuprate anion. The alkyl halide then undergoes nucleophilic attack by dialkyl cuprate anion to form an intermediate which is unstable and thus fragment to give products. Fourth is Frankland's method. When alkyl halide are heated with zinc in an inert solvent, higher alkanes are formed. Alkyl halide heated with zinc metal in inert solvent, alkanes are formed. The reaction is believed to proceed through the following steps. So this is how the reaction will proceed. And fourth is from alcohols. How can we prepare alkanes from alcohols? So the first is the alcohol gives corresponding alkanes on reaction with excess amount of Hi with red phosphorus. The function of red phosphorus is to react with iodine to give Pi3 and thus makes the reaction more forward. Second is the higher alcohol gives lower alkane on reaction with concentrated nitric acid followed by sodium hydroxide and calcium oxide. So this is how the reaction will proceed. Third is the lower alcohol gives higher alkane on reaction with chlorine and light halogenations followed by Wurtz reaction or Corey-House reaction. So this is how the reaction will proceed. And fifth is from ethers. The ethers on reaction with Hi red phosphorus gives corresponding alkane. From methoxymethane we can prepare methane. Decarboxylation is facilitated by the presence of electron withdrawing group such as NO2 nitro group, cyanide group, carbonyl or carboxylic group, etc. Third is the lower carboxylic acid gives higher alkane on reaction with NaOH sodium hydroxide followed by Kolb's electrolysis. Second is Hi with red phosphorus followed by halogenation and Wurtz reaction. So this is how the reaction will proceed. So this is the ninth method how to prepare alkanes from acid derivatives. The acid derivatives in a sense esters, acetamides, acid halides and acid anhydrides. On hydrolysis gives carboxylic acid which on further reaction with Hi and red phosphorus gives corresponding alkane. Second method is sodium hydroxide with calcium oxide and heat gives lower alkane etc. So this is how the reaction will proceed. Its second part is that the acid amides can give lower alkanes on reaction with bromine in the presence of potassium hydroxide and the reaction is termed as Hofmann bromamide reaction followed by reaction with nitrous acid, Hi, red phosphorus and heat. So this is how the reaction will proceed. This is the 10th method how to prepare alkanes from aldehydes and ketones. The aldehydes and ketones on reaction with reducing agent like zinc metal with mercury with HCl and the reaction is termed as Clay-Manson reduction or NS2 with potassium hydroxide which is called Wolff-Kishner reduction or Hi with red phosphorus gives alkanes. So this is how we can prepare alkanes from aldehydes and ketones. Aldehydes and ketones gives lower alkanes on reaction with concentrated nitric acid followed by sodium hydroxide, calcium hydroxide with heat. The aldehydes and ketones gives higher alkanes on reaction with concentrated nitric acid followed by sodium hydroxide and Kolb's electrolysis. So now the 11th method to prepare alkane from Grignard reagent. The Grignard reagent on hydrolysis with water with H positive gives homologous alkane. Grignard reagent on reaction with aldehydes or ketones followed by hydrolysis gives alcohol, which on further reaction with Hi and red phosphorus gives corresponding alkane. The Grignard reagent on reaction with carbon dioxide followed by hydrolysis gives carboxylic acid, which on further reaction with Hi and red phosphorus gives corresponding alkane. So this is how we can prepare alkane from aldehydes and ketones. 12th method is Cracking, the process of conversion of higher hydrocarbons of petroleum into lower hydrocarbons by strong heating is called cracking. For example, an octane on strong heating break down as follows. It is evident that cracking involves the breaking of carbon-carbon bond as well as carbon-hydrogen bonds. The reaction follows a free radical mechanism. The nature of products formed on cracking of alkanes depend upon the structure of alkane, the pressure under which cracking is carried out, and the nature of catalyst. The cracking process is of prime importance for the manufacture of gasoline from high boiling fractions of petroleum. It is also used for production of oil gas from kerosene, which is used in laboratories. So there is changes occurring during cracking. During cracking, following important changes take place. Straight chain alkanes also isomerized into branch chain hydrocarbons. Saturated hydrocarbons are converted to unsaturated hydrocarbons. Cyclic Cyclization of aliphatic alkanes may take place, and cracking leads to formation of a mixture of large number of hydrocarbons, all having lower boiling points than initial alkane. Here is a point to be noted that lower alkanes can be converted into higher alkanes by Wurtz reaction and by Kolb's electrolysis, but methane cannot be prepared by Wurtz reaction or Kolb's electrolysis. Methane can also be prepared by hydrolysis of aluminium carbide and beryllium carbide as follows. So this is the table showing preparation of alkenes in brief. First is alkenes. Reagents required. If we use alkenes and perform the hydrogenation using finely divided nickel metal, platinum or palladium, which is called Sabatier-Sanderson reaction at 573 to 673 Kelvin temperature, then we can get ethane. Similarly, these are the reagents required and secondary reagent and then the product formed. Now the topic is physical properties of alkanes. Petroleum and natural gas are two principal sources of alkanes. Methane is also the principal constituent of marsh gas produced by the anaerobic fermentation of cellulose. Some plant waxes also contain alkanes. For example, wood turpentine or some pine trees contain N-heptane C7H16 and cabbage leaves contain N-nonacosane C9H20. So let's talk about the physical state of alkanes. The first carbon to fourth carbon alkanes are colorless gases. Fifth to 17 carbon chain alkanes are colorless liquid and above that are colorless solids at room temperature. Then we will talk about specific gravity. The specific gravity of alkanes increases with molecular mass and becomes constant at 0.8. So all alkanes are lighter than water. Then we will talk about solubility. Alkanes are non-polar, so they are insoluble in polar solvents like water, but soluble in non-polar solvents. Further, their solubility decreases with increase in molecular mass. Then boiling point. On moving among the alkanes in their homologous series, the size goes on increasing and thus the magnitude of intermolecular van der Waals forces also goes on increasing. So the amount of heat required to break van der Waals forces also increase, hence boiling point also increase. As the alkanes have the zigzag structure and the even alkanes are more symmetric than odd alkanes, and thus the even alkanes have more close packed structure than odd alkanes. So more heat is required to break the symmetric lattice than asymmetric lattice. Hence the increase in boiling point on moving from odd alkane to even alkane is large and from even alkane to odd alkane is very small. In a sense, the boiling point increase non-uniformly on moving among the alkanes in their homologous series. Among the isomeric alkanes, N-pentane has more surface area than neopentane and thus the magnitude of intermolecular van der Waals forces will be more in N-pentane than in neopentane. So more heat will be required to boil the N-pentane than neopentane. Then effect of branching of an alkane chain on boiling point. Branching of the chain also affects the boiling point. Alkanes experience intermolecular van der Waals forces. The stronger the van der Waals forces, the greater will be the boiling point of alkane. As branching increase, the surface area of molecule decrease, which results in a decrease in surface area of molecule. As a result, the van der Waals forces also decrease, and thus the amount of heat required to break van der Waals force also decrease. Hence, the boiling point of alkane decrease with an increase in branching. Uh, So these were the physical properties. Now we'll talk about the chemical properties of alkanes. Alkanes are chemically inert under ordinary conditions and are known as paraffins, as we have talked earlier. Latin param, little. Affins means affinity. The inertness of alkanes can be explained as follows. Alkanes are saturated hydrocarbons having strong carbon-carbon bond and carbon-hydrogen bonds. These bonds are not easily broken by any of the oxidizing agents like KMNO4, K2CR2O7, or reducing agents like lithium aluminium hydride or sodium borohydride, etc. Since carbon and hydrogen have nearly the same electronegativity, the carbon-hydrogen bonds are only slightly polarized. Consequently, they are generally unaffected by most bases such as sodium hydroxide or potassium hydroxide. Since alkane molecules do not contain any lone pair, unshared electrons, they fail to react with Lewis acids. The bond angle in alkanes are 109 degree 28 minutes due to sp3 hybridization of carbon atoms. Since there is no deviation from normal tetrahedral angle, there is no angle strain. Thus, alkanes are quite stable and hence less reactive towards common reagents. However, under strong conditions, alkanes undergo a few reactions such as substitution and thermal decomposition. These important reactions of alkanes are discussed below. So, first one is oxidation. Its first part is combustion. When burnt in an excess of air or oxygen, alkanes undergo complete oxidation to produce carbon dioxide, water, and large quantities of heat. Due to large quantities of heat produced during combustion of alkanes, this reaction has tremendous practical importance. So the second reaction is incomplete combustion. Incomplete combustion of alkanes due to insufficient supply of air or oxygen results in the formation of soot or carbon black. This is used in manufacture of Indian ink, printers ink, black varnish, or as a filler for rubbers. Then it can be of two types. Catalytic oxidation. When heated in a regulated supply of air or oxygen at high pressure and in the presence of suitable metallic catalyst, lower alkanes are oxidized to alcohols and aldehydes while higher homologous yield long chain fatty acids. For example, when a mixture of methane and oxygen in suitable proportions is compressed to 100 atmospheres and passed through copper tubes at 475 Kelvin temperature, methane is oxidized to methanol, as shown. Second one is chemical oxidation. In general, alkanes are inert towards oxidizing agents such as KMNO4 and K2CR2O7, etc. But an alkene containing tertiary hydrogen atom get oxidized by such reagents to corresponding alcohol. For example, we can prepare tertiary butyl alcohol from isobutane using alcoholic KMNO4. Second reaction is substitution reactions of alkanes. Alkanes undergo substitution reactions under different reagents. First one is nitration. Alkanes in vapor state reacts with nitric acid at 700 Kelvin to give nitroalkane as shown. The higher alkanes gives mixture of different products due to breaking of carbon-carbon bonds in alkanes which are difficult to separate, so the yield in the reaction is poor. Second reaction is sulfonation. Hexane and higher alkanes on reaction with oleum, which is concentrated S2SO4 with SO3 gives alkane sulfonic acid as shown. Third one is halogenation of alkanes. The alkanes undergo substitution reaction with halogens in the presence of sunlight to give the mixture of products as follows. Chlorination and bromination of alkanes can take place readily in the presence of light or at high temperatures like 523 to 673 Kelvin. Iodination of alkanes is slow and reversible. It can be made forward by using oxidizing agents like concentrated nitric acid, HiO4, etc., which converts Hi into iodine molecule. Fluorination of alkanes cause explosion due to very high reactivity of fluorine. It can be made less vigorous or reactive by diluting with F2 by diluting fluorine with hydrogen gas. So here is the mechanism of halogenation of alkanes. Halogenation of alkane in the presence of light takes place through the free radical mechanism in the following steps. First step is chain initiation step. In this step, the halogen molecule breaks down to give halogen free radical on heating or by light. It is a dissociative reaction in which change in heat energy or enthalpy change is equal to activation energy. Second step is chain propagation step. In this step, halogen free radical react with alkane molecule to give alkyl free radical and hydrogen halide. The alkyl free radical further reacts with halogen molecule to give alkyl halide and halogen free radical which further reacts with alkane molecule and so on. During chlorination, the transition state reached earlier due to high reactivity of chlorine free radical and it has more reactant character than product character. While during bromination, the transition state reached late due to low reactivity of bromine free radical and it has more product character than reactant character. Third step is chain termination step. In this step, the free radical combine amongst themselves without giving new free radical. It is an associative reaction in which activation energy is zero. So how can we prove that halogenation of alkane propagate through free radical mechanism? So evidences in support of free radical mechanism. Following evidences support the free radical mechanism for the halogenation of alkanes. First one is the reaction does not take place in dark at ordinary temperatures but take place in the presence of light or at temperature 600 Kelvin as a large amount of energy is required for the dissociation of halogen molecules into halogen free radicals. Second is if the reaction actually follows free radical mechanism, the addition of substance which are source of free radicals in a sense. Radical initiators must initiate the reaction below 600 Kelvin in dark. For example, methane can be chlorinated in the presence of tetraethyl lead at 410 Kelvin in the presence of organic peroxide at 298 Kelvin in dark. Now there is effect of tetraethyl lead. In the presence of tetraethyl lead, halogenation of alkanes takes place at a lower temperature in dark. This is because at 415 Kelvin, tetraethyl lead decomposes to give ethyl free radical. This ethyl free radical reacts with chlorine gas to produce chlorine free radical which propagates the chain reaction and so on. Thus the rate of reaction is enhanced even upon addition of small amount of tetraethyl lead. Second is effect of organic peroxide. Like tetraethyl lead, organic peroxide decomposes to form free radicals which initiate the chain reaction as follows. This chlorine free radical propagates the chain reaction and rate of reaction is enhanced. Third is quantum yield. Quantum yield is defined as the ratio of number of molecules reacting to number of photons of suitable wavelength absorbed. For free radical chain reaction, the quantum yield value is generally very large or in other words greater than 1. The high quantum yield supports free radical mechanism since the free radicals once formed react with many molecules of alkane. For each quantum or photon of energy absorbed, many thousand molecules of alkyl halides are formed. It is due to repeating chain propagating steps. Then fourth is role of inhibitor. The substance which slows down or stop the reaction even if present in small amount are known as inhibitors, and the process is known as inhibition. It has been observed that oxygen, if present in the reaction mixture, slows down the reaction. Oxygen is diradical. In a sense, it has two unpaired electrons. Due to the presence of two unpaired electrons, oxygen reacts with alkyl free radical to form less reactive alkyl peroxy free radical, which is unable to propagate the main chain reaction. The two peroxy free radical combine with each other and form the dimer. The rate of reaction will remain slow as long as oxygen is present in the reaction vessel. When all the oxygen added is consumed, then the reaction speed will again be picked up. This on one side proves that the halogenation reaction follows the free radical mechanism, and on the other hand shows that effect of adding some radicals like oxygen, a new reaction starts, which leads to a parallel reaction. Thus rate of desired reaction drops down due to unwanted side reactions. So this is how oxygen reacts with alkyl free radical and form alkyl peroxy free radical. Thus oxygen acts as an inhibitor. The time period during which inhibition lasts and after which the reaction proceeds normally is known as inhibition period. Now there is factors affecting the yield of products formed during halogenation of alkanes. The yield of products formed during halogenation of alkanes depends upon the following factors. First one is reactivity of 1 degree, 2 degree, 3 degree, that is primary, secondary and tertiary hydrogen atom of alkanes. The reactivity order among the 1, 2 and 3 degree hydrogen atom of alkanes is 3 degree, then 2 degree and then 1 degree atom. So the selectivity order among 1, 2 and 3 degree of alkanes is 1 degree, then 2 degree and then 3 degree hydrogen atom. Second is reactivity of halogen. How much reactive the halogen is. The relative rate at which different halogen reacts with an alkane is called their reactivity. The reactivity order among different halogens is fluorine is more reactive than chlorine, than bromine and then iodine, and it can be explained on the basis of change in enthalpy values as shown in the table. Third is reactivity order of halogens towards